Welcome to the Odyssey 6100 series QuickStart Guide. Luna's Odyssey 6100 is an interrogation system that utilizes high-definition fiber optic sensors to measure temperature or strain continuously along a sensor's length. The objective of this video is to cover the basic setup and operation of the Odyssey 6100 platform. To start, we will introduce the main components of the system, then we will cover the basic steps needed to set up for a test, and finally we will show how to take measurements with the system and what the saved data looks like. The interrogator processes optical data from up to 8 active channels on its front panel and converts the optical measurements from each scan it takes into a corresponding strain or temperature measurement. At the back of the interrogator, there are available connections for external triggering and ports for power and USB communication with the controller. A ruggedized standoff cable, either 50 or 100 meters in length, connects the interrogator to a remote module that allows the system to be kept a safe distance from any hazardous experiments. The remote module is where sensor optical measurements are taken and where any fiber optic sensors will be connected to the system. Luna fiber optic sensors use LC/APC connectors, and each come with a flash drive that contains a unique key file used by the controller to recognize the sensor. The controller is where the user communicates with the Odyssey system, sets test parameters, and takes data. Assembling the components is straightforward, and for our test, we end up with this setup for our complete Odyssey system. It is important to note that during assembly, all connectors should be cleaned to remove any dust or particulates that could lower the quality of the optical signal. This can be done quickly and easily by using a cleat-top device. Simply pull back the lever to provide a strip of cleaning material and press the connector face to the surface. Make a quarter turn and drag the connector across the strip. This should be done for all connectors on standoff cables, remote modules, and sensors. For our test, we will be using a sensor that is already instrumented on an aluminum beam that can be flexed to make simple strain measurements. The sensor was bonded to the surface of the beam in the same way that a strain gauge would have been applied. The surface was sanded and cleaned, and then the fiber was bonded down using an epoxy. With our sensor connected and the system set up and turned on, we will now move to the controller to begin preparations for our test. Before we get started, let's do a quick rundown of the controller's user interface so that we can be aware of all the features available when setting up to take measurements. If we go to the top left corner under File, we see that we can save and load configurations, which will remember user preferences such as the operating mode or any trigger options that we set. We can use the Install Sensors feature to import new sensor keys or use the Manage Sensors feature to view all currently installed sensor keys. The Playback Test Data feature lets us run through a test that we've already completed, allowing us to jump to any point during the dataset or change the speed of the playback while viewing the measurements on the screen just as they appeared during the test. Lastly, the Export Test Data feature saves the data to a .tsv file that we can use later for analysis. Under Help, we have resources that can tell us about any new features that the latest software update may have added, as well as several user guides for reference if we ever get stuck. Going over the main tabs, we first have Gauge Plot, which is where we can monitor user-defined points or segments of the sensor if we want to focus on specific areas rather than viewing the entire sensor at once. These individual points will be plotted as strain versus time, rather than how the full sensor data appears as strain versus sensor length. Sensor Plot is where we can see our measurements in real time, either viewing all our sensors at once or looking at them individually. The Trigger Properties tab allows us to customize how we take measurements to best fit our experiment. We can make it so that the system only records a set number of scans when a trigger event occurs, or manually adjust the time interval between each scan if, for example, we wanted to do a long-term test where a measurement only needed to be taken once an hour. The Streaming Properties tab is where we can enable data streaming and where we find the information needed to connect to the data stream. Back at the Sensor Properties tab, we can see our available sensor channels and choose the gauge pitch, which determines the resolution mode that is used during a test. We can see the system is trying to identify the sensor at the channel that our aluminum beam is connected to. What we need to do first is install the sensor key that came with our sensor. We can do this by going to the top left and selecting the Install Sensor feature, which automatically locates our connected flash drive. We open the key folder and select the contained reference file. Once the key is installed, the system will recognize the sensor and we can accept it by clicking the green arrow to begin setting preferences for our test. Before we start taking data, we need to decide which of the 3 operational modes we want to measure in. Each mode has a different gauge pitch, which determines the density of measurements along the length of our sensor. The 0.65 mm mode, for example, has 4 times the measurement density of the 2.6 mm mode, but the trade-off is that these measurements are taken at a quarter of the rate of the 2.6 mm mode. Depending on the type of experiment, one mode may perform better than another. For example, if we are taking data in a relatively static environment where large strain gradients are expected, the 0.65 mm mode would work best due to its higher spatial resolution. If taking data in an environment where vibration could be a concern, or where quick changes in temperature or strain are expected, the 2.6 mm mode would be best due to its higher sampling rate. For our test, we will use the 0.65 mm mode because the way we will be deforming our aluminum beam will be mostly static. If we click the View button next to our sensor, we can get a preview of what our data will look like. We'll usually find that there is already some strain imparted on our sensor. This is because the process of instrumenting a component imparts some strain on the sensor when compared to the unstrained reference that was saved in our key when it was manufactured. If we want to zero our measurements, we can save a tear, and now any changes from this state will be reflected in the data. This tear is saved in the data file and can be very useful in evaluating the residual strains after an instrumented component is processed or tested. At this point, it is usually a good idea to do some form of touch to locate. This process is what orients the sensor to the physical component by defining interesting points or segments which will be useful for data interpretation or analysis. This is most easily done with a Q-tip and a can of compressed air. When the can is held upside down, the spray releases in a supercooled state and flash freezes the end of our Q-tip. When we use it to touch a spot on our sensor, it appears as a negative strain spike that can help us map out where the sensor is spatially on the component. For our aluminum beam, the fiber makes 2 straight passes on both the top and bottom surfaces. So to map the start and end of all of those straight segments, we will need to perform touch to locate on a total of 8 points. This is made easier by using the View Gauges feature, where the controller searches for spikes in the data and marks the location to be added to a gauge repository. This is also how we can set points or segments to be monitored in the Gauge Plot tab that was mentioned previously. With our touch to locate points recorded for later use, we're ready to start our test. First, we will need to arm the system before we can take data. It's important to note that once the system is armed, we cannot change any of the settings such as our trigger properties or sensor tear. If further adjustments need to be made, we need to disarm and then rearm again once the settings are correct. After clicking Start, we will begin recording data, and the live strain measurements will appear in the Sensor Plot tab. As the beam is deflected, we see several features within the plot. The positive and negative strain peaks are located at the base of our beam, where the highest strains occur. The positive strains correspond to the tension the fiber undergoes on top of the beam, and the negative strains correspond to compression under the beam. In the 0.65 mm mode, we are still taking data at 62.5 Hz, so even when the beam is rapidly flexed, the measurements are able to easily keep up. Once we have all the data we need, we can end the test by pressing Stop. Lastly, let's take a look at the .tsv file that's generated when we export the test data from the controller. After exporting, 2 files will be generated: a full data file that contains measurements from all locations along the fiber, and a gauge file with only measurements from the user-specified gauge locations chosen during touch to locate. When opening either file, you will find metadata at the top, such as the mode settings used during the test, serial numbers for the sensor and interrogator, and other useful information for record keeping. We can find the tear values used for the test recorded here, allowing us to see the offset used at each gauge location. The physical location of each gauge along the sensor is also recorded along the x-axis row, and underneath that we have the strain or temperature measurements at each location with a universal timestamp for when each scan occurred. This concludes the Odyssey 6100 series Quick Start Guide.